The bond dissociation energy is the energy that is needed to homolytically cleave a covalent bond. Imagine that we have a molecule AB here and we want to break the bond between the molecule. Remember that when we are breaking a bond homolytically, one of the electrons will go to the A and one of the electrons will go to B, and that's why we use this type of arrow. So A will end up with one electron and B will end up with that electron. To do that, we require energy. We need to put energy to break that bond. And so that energy that we put, it's the enthalpy, right? So the bond dissociation energy is the enthalpy that we need to break that bond. So when we are putting energy to break a bond, that is an endothermic reaction, and that's why the sign of the enthalpy will be plus, because we are putting energy into that reaction. On the opposite, when we are forming a bond, right, by combining these two electrons, a bond will form that will result in an exothermic reaction and it will release energy. So when the bond forms, you get the HH bond plus energy, and then that results in an exothermic reaction with a negative sign because energy is released. You've seen this in general chemistry before. Here you have a list of some of those energies, right? So the bond energies to form or to break some of these more common bonds. So the bond dissociation energy is related to bond strength. So how is that? When we look at a molecule just like this one, you know by now that CH3 and F has a very strong bond because F is small, so the protons in the nucleus can interact closely with the electrons that are on the bond. However, for a bigger element like iodine right here, because iodine is much more bigger than fluorine, what happens is that the nucleus is farther away from the electrons on the bond and it cannot keep them so closely. So it's easier to break a CH3I than it is to break a CH3F bond. And the numbers here express that. So as we go down and the halogen becomes bigger and bigger, the energy that you need to break that bond will be smaller. So as we increase the size of the halogen, the bond strength decreases, right? So this is the strongest bond and this is the weakest bond. So one more time, when we have the CH3F, F is smaller, so it can keep the electrons close together. When we have here the CH3I, this is really big. So the electrons that are here in the nucleus are not so close to the electrons that are here in the bond, so it cannot keep them so closely together. So this bond right here is easier to break than this bond right here. And that's why we need to put less energy. Look at this number right here. We need to put less energy to break that CI bond than we have to put to break that CF bond, right? Because remember, we're looking at CF versus CI. And you know this from organic chemistry, from general chemistry, sorry, that we can calculate the bond dissociation energies by combining all the bonds that are being broken and all the bonds that are being formed, and in that way we can get a general enthalpy change, right? So by combining the sum of the bonds that are being broken plus the sum of the bonds that are being formed, right? Remember, this will have a negative sign, right? Because when that will have the negative sign, so we can get the overall enthalpy change. So let's look at an example right here. When we have this reaction right here, so we have a CH bond, a Cl C bond that is being broken. And then we will also have this bond that is being broken right here. And then a new bond forms between the C and the O, and a new bond forms between the H and the Cl. So these are the two bonds that are being broken, the CCl and the OH. And here are the two bonds that are being formed, the CO and the HCl. We go to the table that I showed you earlier, and we can get that the energy that you need to break the bond between a C and a Cl, that's 331. The energy that you need to break the HO is this number right here. And then on the other side, we get the energy that it's released, and that's why we have negative signs right here. We get the energy that gets released when we form these two new bonds. We sum the bonds that are being broken, we sum the bonds that are being formed, we add them together, and then we get an overall minus 3 kilojoules per mole of this reaction. So because we end up with a negative sign, that means that our reaction is exothermic. So overall, we have bonds being formed, bonds that are being broken, but overall the reaction is exothermic. There are some limitations to these bond dissociation energies. So what the information that we can get is from the start and to the end, but we don't know anything about how this reaction proceeds. So we don't know if this reaction will have intermediates or if this reaction will be faster or slower. We can only know the beginning and the end of it. Also, another thing that you have to realize is that bond dissociation energies are determined for gases, and reactions usually happen in a solvent. So even though they are a good approximation, they are not perfect, and they have some limitations, because when you use a solvent, we have to consider other issues like solvation energies. And even though it's not great, it's not perfect, it gives us a very good picture of what are the energy changes that are going to happen in this reaction.